Okay, I want to discuss this paper real quick. It's a very easy paper. It's only 2 pages. A 2-page paper. This is Mumberg, Muller, and Funk 1994. Okay, so this is in your handout. So if you look at your handout, this is at the end, this paper. It's only 2 pages. It's very easy to understand. So I want to talk about the figures. I want to explain this paper. Okay, so the title is Regulatable Promoters of Saccharomyces cerevisiae, Comparison of Transcriptional Activity and Their Use for Heterologous Expression. So the idea is in 1994, researchers needed tools to work with or to work in yeast. Okay, so someone had to actually build these promoters. Someone had to build these plasmids. Okay, somebody has to like do the work and put together these plasmids. And this is one big paper where they did this from Mumberg, Muller, and Funk. So let's look at figure 1. Okay, so let's define the things we need to know to understand this figure. Okay, let's define a few things. Met is the methionine promoter. Okay, so there's a gene MET25, and that makes methionine, the amino acid. Okay, and it has a promoter, and they are taking this promoter MET25, okay, and they are inserting this into a plasmid. They are inserting this promoter into a plasmid. And methionine, let me ask a question. If you have lots of methionine, should you turn the MET25 gene on or off? Okay, so remember, I'm going to say again, MET25 makes methionine. MET25 makes methionine. So if you have lots of methionine, should you turn the MET25 gene on or off? Write it in the chat. On or off? Very good. Very good. Yali Feng. Very good. You want to shut it off. Okay. If you have lots of methionine, you want to shut it off. Okay. So methionine will repress the MET25 promoter. Now there's probably a transcription factor. Okay. There's probably a transcription factor that binds methionine. Okay. And that shuts the gene off. This is just like the trip promoter, and just like it's similar to the arabinose and the lac promoter. Okay, so they wanted to put this plasmid, which is repressible, they wanted to put this promoter into a plasmid. Okay, so let's look at this data from figure 1. Okay, the y-axis is beta galactosidase. We know what this is. We know what beta galactosidase is. Beta galactosidase is a gene from the lac operon. Okay, it's lac Z from the lac operon. We know that. Okay, and there's this interesting chemical reaction. I got it up here. This. Okay, lac Z, beta galactosidase. It can take a chemical called X-gal. Okay, and it can digest it, and it makes blue. Okay, so just know that beta gal plus X-gal equals blue color. Remember this. Okay, you see this a lot in all kinds of papers, in all kinds of research. This is used as a marker in many research papers. Okay, so don't forget this. Beta gal plus X gal equals the blue color. So on the y-axis, what they're measuring is how much blue. How much blue color. Here, it's real dark up at the top, and on the bottom, it's real light. Okay, that's what they're measuring. So what they did is they built a plasmid. They built a plasmid that has lac Z, in front of the promoter for MET 25. They built this, okay? And now they're testing it. And they built two different versions. 416, so this is Plasmid 416 MET 25. The 1 means it's a centromeric plasmid, okay? And in this one, Plasmid 426 MET 25 means it's a 2 micron plasmid. So this is a high copy, 60 copies, and this is a low copy, 1 to 3 copies. Okay, so they built two plasmids, and the difference between the plasmids is one is 2 micron and the other is sen. And this one is this is P416 MET 25, and this one is P426 MET 25. Okay. Now let's look at the x-axis. The x-axis is adding methionine. Okay. So as methionine goes up, blue color goes down. This shows you that methionine is shutting the gene off. Okay. That's what this graph shows. And this graph shows. As methionine goes up, the blue color is going down. Therefore, methionine is shutting this promoter off. So methionine shutting this off and this one off. And let's look at the numbers on the y-axis. So here they're 10, 20, 30, 40. Here it's 100, 200, 300, 400, 500. So this one on the bottom is way more blue, is more blue than this one. And that's because this one is the 2 micron, the high copy. So there's 60 more copies of LAC-Z. And in this one, there's only 1 to 3 copies of LAC-Z, okay? So this is how you understand this data. Okay, let's talk about figure 2, okay? Here they're analyzing. So this paper is about analyzing different promoters. This paper is about finding good promoters for protein expression in yeast, okay? So the ones that they've tested are MET 25, and they also test this other promoter, Gal-S, Gal-L, and Gal-1. Gal-1, Gal-S, and Gal-L. Gal-1 is the promoter I said, the galactokinase promoter. So glucose shuts it off, galactose turns it on, okay? So this is the promoter for galactokinase. And Gal-S is a mutated Gal-1. And Gal-L is also a mutated Gal-1. All right, so let's look at this graph. Glucose is this one. So in glucose, it's off. And in galactose, it's on. Okay, so for each of these, there's a split. So let me ask a question. Which promoter is the most powerful? Which promoter is the most strong? Gal-S, Gal-L, or Gal-1? Write it in the chat. Which promoter is the most strong? Gal-S, Gal-L, or Gal-1? Write it in the chat. Good. Very good, Zhangmin. Gal-1. Good. Gal-1 is the most strong because look, in this case, it's the highest, okay? But what about this? What's this? This one is 416, 426. So this is a sen. This is a sen plasmid, and this is a 2 micron plasmid, okay? So a 2 micron plus the Gal-1 promoter is the best expression. The best expression, highest, okay? But Gal-1, so this one, or Gal-L, these might still be useful. These might still be useful if you don't want too much expression. It's like if you have like piece of meat. So like a steak equals meat. And if you have sodium chloride, salt, some people like to add salt onto their meat, okay? But too much salt, that's bad. Ick. It's bad. It's gross. So this is an analogy. Analogy. Okay. There are situations where you might want a lot of expression, or there are situations where this may be too much. And then in that case, you might want the Gal1 or the Gal-L or the Sen plasmid versus the 2 micron. Okay. So this paper develops different plasmids and different promoters for various levels of expression from low to high. Okay, so let's ask a question. Which plasmid will express insulin more? P416 Gal1 or P426 Gal1? This should be lowercase p. Write it in the chat. Which plasmid will express insulin more in yeast? Good. 426 Gal1. Good. Okay. Let's do the final figure from this paper. Figure 3 is a plasmid map. Okay, figure 3 is a map. These are all the variations they built. Okay. They built plasmids with different oxytrophic markers, a his, a trip, a lu, a ura. Okay. And actually, this third number, codes for the amino acid. 4 codes for trip. 5 codes for lu. But you don't have to know that. You don't have to know the number. Don't memorize that number, but just know that 6 means ura, 5 means lu 2, 4 means trip 1, 3 means his 3. Okay. And they also did different origins. Sen 1 versus the 2 micron 2. Okay. And they did different promoters. Okay. And these are the promoters they analyzed. MET25, Gal1, Gal-L, Gal-S. Okay. So this is the nomenclature. Okay. So let me give examples. Example. P413 MET25 equals Sen, his3 oxytrophic marker, and MET25 promoter. Example 1. Example 2. P426 Gal1. This is a plasmid, 2 micron origin. 6 is ura3 cassette selectable marker with Gal1 promoter. So now we understand how to read yeast plasmids. Okay, this is common for yeast plasmids. And this is an example of plasmid nomenclature. Okay. All right. Let's look at our plan. We discussed Mumberg and Funk. Okay. If there are no final questions, I hope everybody has a great day. Thank you. Everybody have a good night. Goodbye.
I shall meet death head on. Decker Cage, you've got to get out of here. Beware foul demons and beasts. There are many foes here. The time time.